Hi everyone, and welcome to another episode of Organic Chemistry with Wikipedia. Today we'll be starting a new unit on alkenes and alkynes, specifically talking about their structure and naming. So first things first, what are alkenes and alkynes? Alkenes, they look like alkanes, but the kene ending means that you have at least one double bonded carbon. The kyne ending means you have at least one triple bonded carbon. All right, so just to get right into it, the naming of alkenes, very similar to alkanes. You find the longest chain of the carbons that contains the double bond. Here, your carbon chain has to contain the double bond, which means it may not be the longest carbon chain. So even if you have a chain that's longer, if it doesn't contain the double bond, then you can't name it that way. And then you use the prefix that corresponds to the number of carbons in the parent chain, and then we end it with an ENE ending. So then we number the carbons on the parent chain, starting with the end that gives the lowest number for the first carbon in the double bond. We use all of the substituent rules from alkanes. And then you put the only thing that's different is you then at the end, when you're done with all the substituents, you add a number to right before you write the name of the parent chain, indicating where the double bond is. The only exceptions to this are ethene and propene. They don't need number designations because ethene you can only put the double bond in between the two, so there's nowhere else for it to go. I guess I should probably finish drawing this. Since it's nowhere else for it to go, there's no need for a designation. And then the same thing with propene. It's got 3 carbons. So if you write the double bond going this way, it's on the first carbon. If you write the double bond going that way, it's on the first carbon, so it doesn't really matter how you write it. There's only one possibility. So those are the only 2 that don't need number designations. Okay, common names. So there are a couple names that are common that you will see here and throughout that we do need to know the names of. So we just said that this was ethene, but this is actually ethylene, is the common name for that. Propene with 3 carbons, common name is propylene. I know it's crazy how the common names are longer than the actual IUPAC names. Whatever. All right, and then lastly here we have this thing that looks like an isopropyl alcohol, but it is not. This is what we call isobutylene because it's got that iso structure and a double bond and 4 carbons, and so, it's pretty self-explanatory. All right, so let's take a look at some examples here. We'll start off with something very, very easy. So here we have a double bond. It's on the first carbon. So that makes that really easy. 6, 7. So here we have 7, so this would be heptene. And then because it's on the first one, I would put 1 heptene. Sometimes you will see it written as hept-1-ene. Both of these are acceptable. It doesn't really matter how you write it. I'm not a huge fan of writing it like this because it bothers me to have a number in between a word, but that's just me. So if you see this, in your studies or whatever, this is a perfectly acceptable way to write it. I will be writing it where the double bond number goes in front of the name, but you are, again, free to do it this way. Whatever floats your boat. Okay, so here we are wanting to find the longest carbon chain. So I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. And then 1, 2, 3, 4. I can't do it even if I wanted to this way because it doesn't contain the double bond. So I'm going to go 1, 2, 3, 4, 5, 6. So my carbon is on, or my double bond is on my first carbon here, and I have a methyl group on the fourth. So this would be 4-methyl, 1 hexene. All right, so next up here we have an example of what I was talking about. We have 1, 2, 3, 4, 5, 6. So the longest parent chain is 6 carbons, but it doesn't contain the double bond. So the double bond would be 1, 2, and then I could go 3, 4, 5, 3, 4, 5, 3, 4. I'm going to go 3, 4, 5, and it doesn't matter which 4, 5 you choose because it's the same thing. All right, so here I have 2 ethyl groups here, so I have 2, 3 diethyl And then my double bond is on 1, and this is 5, so this would be pentene. All right, next up we have this guy right here. So here we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. It's the same thing. So we'll go 1, 2, 3, 4, 5, 6. So we'll go 1, 2, 3, 4, 5, 6. All right, so what I've got here is a methyl group on number 2, an ethyl group on number 3, and a bromo group on number 4. So I'm going to start here with the bromo because it's first in the alphabet. All right, pen will start working immediately. There we go. 4 bromo, 3 ethyl, 2 methyl. And then my double bond is also on the second carbon, so this would be 2, how many do I have? 6 hexene. 4 bromo, 3 ethyl, 2 methyl, 2 hexene. All right, spectacular. All right, so let's talk a little bit about shapes here. So according to Vesper, the molecules that are trigonal planar, meaning they have 3 things attached, so each of these carbons in this double bond would have 3 things attached to it. Why doesn't my pen work? Here we go. It has 3 things that are attached to it. 1, 2, 3 on this one. 1, 2, 3 on this one. Even though the bond angle is supposed to be 120, and it's less if it's lone pair, here we find that the bond angle is a little bit larger than 120. Here it's 121, and then the more substituents you add, the greater the bond angle gets because the farther it wants to be away from that double bond. So that's all that there is about that. Electron repulsion, hip hip hooray. Okay, so we talked briefly about cis-trans isomerization when we talked about single bonds because, and then we can only have that happen when we had rings because all other single bonds have free rotation. This double bond, as it turns out, does not have free rotation. The double bond carbons are constricted, so you can have cis-trans isomerization around a double bond. So if you have both of the substituents on the same side, those are cis, and if you have them on opposite sides, those are trans. So again, cis is when you have both on the bottom of the double bond or the top of the double bond, and then you have the trans being on either side of that double bond there. All right, so if we are looking for what is our designation, we want to look at the parent chain, and then from the parent chain, we can kind of draw arrows and figure out what's going on if we can't easily see what's happening. So if I have something like this, if I have that, and let's put a double bond here. All right, so if we look at this, so here's our double bond, right? And so with our double bond, this is going that way, this is going that way, so they're opposite directions, so this would be trans. And then exactly the opposite if you had... and then here we have the same kind of compound here. And so if we draw, here's our double bond. And so we're going up and we're going up. So this would be cis because they're both on the same side. All right. So let's take a couple look at a couple examples here. Did I skip something? I did. If we don't use cis-trans isomerization, we can also use something called EZ isomerization. This EZ notation is used a lot when you have a bunch of different substituents to figure out the order in which you label them. Because like if we look here, there is there's a bromine and a chlorine here, and then if there were 2 hydrogens down here, we could just say this was cis, but then this is a fluorine here. So like, is this cis because the bromine and the chlorine are up here, or is it trans because there's a chlorine and a fluorine here? Like, how does that work exactly? So to alleviate that sort of stress, we use EZ isomerization here. So the one with the highest priority is the one with the highest molar mass, is on the first carbon, and then the one with the highest priority of the second carbon is going to be the one that has the higher molar mass. So between bromine and fluorine, bromine has the higher molar mass. Between chlorine and hydrogen, chlorine has the greater molar mass. So since they're both on the same side, this would be, we would consider this to be cis. But when we're looking at easy isomerization, the Z means that they are together. So this would be cis or this would be Z. And then if we were looking at here, the bromine is the higher of the two and the chlorine is the higher two here. So they're opposite. So this would be E. So this is E is sort of trans, and then cis is going to be the together one here if they're both on the same side. All right. And so again, if we look at our priority with our molar mass, then it just makes life a little bit easier. All right. And like, so if we look here, you know, with cis and trans, it's just easy to see because we have like CH3 is our substituent here and H is here. So CH3, I mean, obviously the molar mass of CH3 is greater, but it would be like 12, 13, 14, 15. And this is 15, and this is 1, and this is 1. So the two higher ones are on the bottom. So this would be Z, and then these the opposite. So this would be E. Okay. All right. So now let's look at some examples. All right. So if we look here, we have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. All right, so if we go this way, 1, 2, 3, 4, this would be the fourth carbon, 1, 2, 3, so this is the third carbon, so I'm going to go 1, 2, 3, in this direction, 1, 2, 3, 4, 5, 6. Okay, so if we're going to label this, so there is nothing over here, so the highest substituent on this side is on the bottom here. And then over here, I have a methyl group, and I have 1, 2, 3 carbons, so this is kind of like a propyl group. So this is the main chain here, so this main chain is going down. Both of them are going down, so this would be trans. Nope, just kidding. Cis. And then if we're going to label these, what do we have here? We have a methyl group. So this would be 4-methyl, 3-hexene, or this would be Z, 4-methyl, 3-hexene. And the EZ is used more for something called chirality, which we don't cover in this class, but you will cover it in organic chemistry. So it's just kind of nice to have been able to see it and look at it to figure out what's going on. And this is actually, I just realized there's a 7th carbon here. So this is not hexene, it's heptene. Well done. Heptene. Okay. All right, we have one. Let's look at this next one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3. 1, 2, 3. So it doesn't really matter which way. So I'm going to pick this way since I encounter a substituent here. Since it doesn't matter which side you pick the double bond on, I'm going to pick whichever makes the substituent better. Okay, so here I have, there's only one substituent on each of these. So this is going up, this is going down, so this is going to be trans, 2-methyl, 3-hexene, or E, 2-methyl 3-hexene. All right, last up, this one's a little complex looking. I'm going to start over here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. It doesn't really matter. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. All right, so if I look here, my main chain is going down, which is going to always have the greater mass than just a substituent here. So this is coming down. And then here, there is no difference between these two things right here. So if there's no difference, it doesn't matter which one's on top and which one's on the bottom. So that means that there's actually no isomerization here. If the top and the bottom don't matter, we have, like, it just doesn't matter. So we have one going down, but then the other one doesn't matter. So we don't have cis-trans isomerization for this particular compound. So we would just draw this as we normally do. This is an ethyl group, this is an ethyl group, and this is an ethyl group as well. So, right, so this is going to be 3, 4, 6, tri-ethyl. And then what do we have here? This is 3, and then 8 is octene. All right. Okay, so cycloalkenes. Cycloalkenes are very similar to cycloalkanes. The prefix that corresponds to the number of the ring, and then its prefix, and then we just add an ene here. We want to put if they're substituents, we number the carbons such as the double bond is the first and second carbon. And then if we pick, like, we go clockwise if we encounter the first substituent with a lower number that way, or we go counterclockwise if the substituent's on the other side. And then you just follow the rule for cycloalkanes. All right, so here if we look at this, so we're always going to make our carbon double bond the 1 and the 2. So 1, 2, 3 over here, or we can do 1, 2, 3 over here. This is methyl, and this is isopropyl. So I comes first. So I'm going to do that one here. So this is going to be 3 isopropyl, 4, 5, 6. 6 methyl cyclohexene. And there's no need to put a number here because we always designate the first and the second as where the double bond is. All right, so here we have 1, 2, and we counter the double bond, or we have 1, 2. So this would be 1, 2, and this would be 1, 2. So I'm going to go with 1, 2, 3, 4, 5. All right, so this is a sec-butyl group. Sec-butyl, and so the sec doesn't count, so this would be first. So this would be 4 sec-butyl, 1, 3 difluoro cyclopentene. All right. So that's that. Polyenes, this is when you have multiple double bonds in a chain. We're only going to deal with dienes and trienes, so when you just have 2 or 3 double bonds. So we do the same thing that we've always done, and then to name the compound, we just designate what numbers each of them are on, separated by a comma. All right, so let's take a look here. Here it doesn't matter what we use to, or what side we start on. We have 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Makes no difference. So we have on the first carbon and on the fourth carbon. So this is going to be 1, 4, and then this is, nope, penta, just kidding. Pentadiene. And you don't have to put that little dash there if you don't want to. Sometimes it will also be written this way, 1, 4 diene. Either one of those is fine. I don't like to break up words, but since there's already a dash here, I guess it doesn't really make any difference. Or you don't have to put the dash at all, actually. I did say that, didn't I? So you could just do this. Whatever floats your boat. All right. So here again, we have 1, 2, 3, 4, 1, 2, 3. So this is 1, 2, 3, and then this is 1, 2, 3. It's the same one, but the substituent is over here. So this will be 1, 2, 3, 4. All right, so I have 2 methyl, 1, 3 butadiene. Here we go. Lovely, lovely, lovely. And then here, when you have cyclos, you do have to number them because there's 2 of them. So we'd go 1, 2, 3, or we'd go 1, 2, 3. It makes no difference. 1, 2, 3. So this would be 1, 3, cyclopentadiene. And there you have it. All right. Last but not least, naming alkynes. Alkynes are the least common of all of the things that we encounter, just because triple bonds are not super duper predominant in nature. Same exact rules as alkenes, except you replace it with a YNE instead of an ENE. Same exceptions to the designation of the double bond with the triple bond. If you have the triple bond, it can only be in one place. Same thing goes with propyne. It doesn't matter if you draw the triple bond first or second, it's always on the first carbon. So those are the only ones that don't need number designations, just like in alkenes. All right, so common alkyne names. This should be ethylene, but this is actually called acetylene, like an acetylene torch, in case you were curious. It's exactly what that is. So this is called acetylene. Instead of propyne, this is called methyl acetylene. I know. Common names are annoying. And then here, instead of being called 2-butyne, 1, 2, 3, 4, 2-butyne, this is, you guessed it, dimethyl acetylene. Really good times. Really, really good times. All right, and then just looking at some examples here, we start with the triple bond, 1, 2, 3, 4. So we've got 3-methyl, 1 butene, not butadiene, butane. And then here we have 1, 2, 3, 4, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So we have 6,6-dimethyl, 3-heptine. All right, and then cycloalkynes, same thing as the cycloalkenes, except it's cycloalkyne and not cycloalkene. And then this is, again, super duper rare, not very often seen. So we have 1, 2, 3, 4, 1, 2, 3, 4. Here we have an isobutyl group, and here we have a methyl group. So isobutyl takes precedent. So this will be 1, 2, 3, 4, 5, 6. So I will do 4 isobutyl, 5 methyl, and then this is cyclohexyne. Excellente. All right, so that's all that there is to naming and structures of alkenes and alkynes. This has been another episode of Chemistry with Wikipedia, Organic Edition. I hope you learned something, and until next time, keep on chemin'.